Good evening, everyone. Thank you for joining us tonight for our stargazing lecture, a kind of a special stargazing lecture. Typically, we host these events once a month on Friday nights, and we actually had one just last week on dark matter. But there was such a notable discovery and breakthrough that we were forced, really, to have a special event this week consistent with that discovery that was announced just yesterday in the news. Hopefully you guys had the opportunity. Did you see something in the news about this recent announcement? Excellent. So I'm Dr. Cameron Hummels. I'll be your MC for this evening's event. And just a quick layout of what the timeline will be for our program tonight. In a couple of moments, I'll introduce our speaker, who's going to talk for about 30 minutes on the topic that you probably read about merging supermassive black holes and how we discover evidence of these merging supermassive black holes from monitoring pulsars, these dead stars around our own galaxy. So that'll be about 30 minutes. And then we'll take only a couple of questions from the audience, and then we'll immediately kind of transition to two different things. In here, we'll bring this table forward and we'll have a panel Q&A consisting of the speaker and several other members of the department specifically working on the topic of this scientific breakthrough that was just announced. So members of the science team responsible for that scientific discovery will be answering questions related to that. I mean, you can also ask random astronomy and physics questions, but just to let you know that the specialty of the members of the panel will be people who worked on this particular project. And then at the same time as that, we have telescopes set up on the fields directly behind us. So there will be 3 telescopes set up, one probably pointed towards M101, which is the Pinwheel Galaxy, where there was this recent supernova that happened in the last couple of months. You can still see evidence of the brightening of that exploding star. And the moon, of course, is quite bright tonight, so we'll be looking at that with one telescope. And we might switch around. There might be an opportunity to look at M87, which is this enormous elliptical galaxy that harbors one of the biggest supermassive black holes in the local universe. In fact, it's the one that was announced maybe 4 or 5 years ago that we'd taken a picture of a black hole, if you remember that from the news. We won't be able to see the black hole with our smallish telescopes out here, but you should be able to see the galaxy itself that harbors that black hole. As I said, these events happen once a month. Here, we've been doing them for almost 7 years. They're always recorded and streamed on YouTube. In fact, we're streaming on YouTube right now. So if you missed something during the lecture, or you want to go check something out from tonight or any of our previous events, I encourage you to look up Caltech Astro on YouTube, and we have tons and tons of content from previous lectures on a variety of different topics. In addition, we have a sister series of events called Astronomy on Tap that take place at a local bar and restaurant in Old Town Pasadena called the Dog House. These events take place on Monday nights. Our next one is July 17th, so a few weeks away. And it's a little bit less formal because, of course, you're in a restaurant instead of a university. And it features 2 15 to 20-minute science talks given by local researchers, either at Caltech or NASA Jet Propulsion Laboratory or the Carnegie Observatories or various different astronomical institutions in the Los Angeles area. And then we have astronomy-themed pub trivia. We have live rock music. It's really fun, and I encourage you to check it out if you haven't. It's like these events. It's totally free, and it's open to everyone. And even though it's a bar, it is all ages. So children can come. They just can't drink alcohol. So I think those are my main announcements for tonight. It's my pleasure to introduce our speaker representing the NanoGrav Consortium. So Dr. Aaron Johnson joins us. He did his undergraduate studies and his graduate work both in Arkansas before he did postdoctoral work at University of Wisconsin-Milwaukee. And then he joined the department here at Caltech in the last year and has been doing some great stuff with the NanoGrav team that just got announced and we're going to hear all about tonight. So please welcome Dr. Aaron Johnson.
All right, thank you. I'm very glad to be here tonight to talk about this result, which many news outlets have picked up to my surprise. But yeah, this has been really great, and we have a fantastic result, which I would really like to talk to you about tonight. And for the next 30 minutes, I will try to I will endeavor to explain what this result, or how it was found and what it means. All right, so in this result, the most important, the three big players are, of course, supermassive black holes, up in the upper left here, neutron stars, and gravitational waves. Okay, we use all three of these to find evidence for a gravitational wave background, which we'll talk about in a moment. First, let's start with black holes. All right, so we're standing here on Earth. If you throw an object up in the air, it sort of goes up, it stops at the top, and then it comes back down, right? But if you throw an object up at 25,000 miles per hour, it turns out that it will not come back down. It will actually orbit the Earth. And so, for example, this picture was taken by NASA and the Apollo 17 crew. And so they clearly have escaped the Earth, and they've reached, at minimum, the escape velocity. Okay, and so if you shrink the Earth down to the size of a penny, and this is to scale, okay, all right, so we've zoomed in a little bit. All right, so if you shrink the Earth down to the size of a penny, then it turns out that if you could make a rocket on that penny and launch it as fast as you wanted to, it doesn't matter how fast you go, you could never leave the surface of that penny. And the reason is because the escape velocity is now the speed of light. So you would have to travel faster than the speed of light to get off of this penny-sized Earth. And the reason is because we've condensed the Earth's mass down into something that's small enough that the gravitational pull is so strong that it's become a black hole. Okay, and so this, when the escape velocity becomes that the speed of light, we have a black hole. We can no longer escape from that object. How big do these things get? And this is fantastic because Cameron just mentioned M87, and so I picked M87 for this one. The Event Horizon Telescope collaboration took a picture of this just a few years ago, and this one, it's about 50 million light years from here, but it's huge. It's 6.5 billion suns. Okay, it has the mass of 6.5 billion suns. And we typically find these things at the center of galaxies. And so if you have many, let's say you have two galaxies, they may interact and eventually fall toward each other and collide, just like Andromeda and the Milky Way will do in 4.5 years. So the Milky Way galaxy is where we live. And the, so this,
4.5 billion.
4.5.
You said 4.5 years, that's what.
Sorry, 4.5 billion years. Okay, my mistake, yes. Okay, yeah, so the... I gotta get my affairs in order. So, yeah, right. All right, so if these, let's say, many galaxies that we see have supermassive black holes at the centers of them, and so if these two galaxies merge into one, then we have one galaxy with two supermassive black holes in it. And eventually, those supermassive black holes will move toward each other through many different processes, which which are not a part of this talk. But you can get these. Eventually, you find that these supermassive black holes will be close enough that they emit significant amounts of gravitational waves. Okay, but before we talk about that, I want to talk about neutron stars. All right, so neutron stars are the second densest objects in the universe. They are the densest objects with stable matter configurations, meaning that if you add too much mass to them, they will collapse into a black hole. And neutron stars typically have a mass around 1.5 times the mass of our sun, and they've been compacted down into the size of a city. Okay, and so here I have a neutron star which is hovering above Pasadena, and so you can sort of get a sense for the scale of how small these things are, but they have more mass than our sun. So they're really extreme objects, and some of these objects are actually what are known as pulsars. Okay, and so pulsars have magnetic fields and radiation that emits along the axis of that field, and so what will happen is these things rotate, and it will rotate, swinging that beam around, and occasionally, if it's oriented the right way, will hit us here. And so we get radio emissions that we detect in our telescopes, in our radio telescopes here on Earth. Okay, so now I want to move on to gravitational waves. Okay, so in this image, we have two black holes which are orbiting each other, and you can see these green swirls going out, and those are the gravitational waves, which are ripples on the fabric of space-time. And then, of course, once they merge, it has an enormous emission of gravitational waves. And this is akin to the situation of a disturbance on a lake. So let's say you drop a bit of water, you have these ripples that travel out across the lake. Okay, gravitational waves travel at the speed of light. Of course, the lake situation, that one does not travel at the speed of light, but yeah, so originally predicted in about 100 years ago by Albert Einstein. What effect do gravitational waves have? So let's hit Einstein with some gravitational waves. Okay, so the effect here is to make him tall and skinny, and then short and fat, and tall and skinny and short and fat, and over again. So if the gravitational wave is passing through the screen here, and we've greatly exaggerated the effect, normally these are very tiny, very small effects that we have to use very sensitive instruments for, you get this stretching and squeezing motion. Okay, so these are the very sensitive instruments which detect gravitational waves. And so LIGO regularly detects gravitational waves when they're online, and they use an observatory in Hanford, Washington, and Livingston, Louisiana. The way that they do this is by, you see these arms that are stretched out towards the top of the screen there. Those are about 2.5 miles long, and any stretching or squeezing that happens due to a gravitational wave on that arm is going to be picked up as gravitational waves. They'll be detected. Okay, so this happened on September 14th, 2015 for the very first time. LIGO directly detected gravitational waves because, so in this video, we have two approximately 30 solar mass black holes orbiting each other and then eventually merging. If we wait a second, it'll come back around. Okay, so this opened a new window on our universe. Previously, we had only looked at the universe through light that we see with our eyes or somewhere on the electromagnetic spectrum. And in this case, now we can see the universe with gravitational waves. Okay. Yes, so gravitational waves and light are very different. And it's a different way to study the universe. But I wanted to mention this because it is important for the talk. So you notice that the visible light spectrum there, that's what we see every day. If you've ever had a sunburn, you've had too much ultraviolet light hitting you. If you've ever broken a bone, perhaps you've been exposed to X-rays to try and identify where your bone break was. Microwaves will heat your food. And in the very long wavelengths, so you can see that there's a wavelength chart here. On the left side, we have very long wavelengths, and on the far right, we have very, very short wavelengths. And so this one on the far left is the radio waves that your cell phone may use. And those are the ones that we'll be interested in using in pulsar timing. Okay, so the gravitational wave spectrum is similar. It has many different frequencies, many different wavelengths that you can look at here. So LIGO detection was in the high frequency regime. So you can see over there ground interferometers. That's where LIGO resides. And the one that we are interested in, so those LIGO detects masses of 1 to 100 times the mass of our sun in black holes. And the one that we're interested in are supermassive black holes, supermassive black hole binaries in particular. And so the bigger the mass, and these are millions to billions of times the mass of our sun, the bigger the mass, the lower the frequency. And so if you move over to the left of on the left of the plot here, you have supermassive black hole binaries, and you can use pulsar timing to do this. And so the collaboration that I'm a part of is known as NanoGrav. And this is a pulsar timing array collaboration, and we'll talk about what an array means in just a moment. There are about 200 members of NanoGrav, and it's about 70 different institutions across the US and Canada. Oh, I should mention nanograv stands for North American Nanohertz Gravitational Wave Observatory. So we use radio telescopes to time pulsars. We'll talk about what that means in a moment. And in particular, we use the Green Bank Radio Telescope, Arecibo Observatory, the CHIME experiment in Canada, and the VLA, or the Very Large Array in New Mexico. Okay, and so each of these are sensitive to radio emissions from pulsars. Okay, so we can pick up pulses from those pulsars, and each time that we do, each time this thing hits the screen, you get a new data point in your radio telescope. Okay, now we use very fastly spinning pulsars, which are known as millisecond pulsars. So that means that their spin periods are milliseconds, or on the order of milliseconds, which is very fast. It's faster than your kitchen blender. So instead of just this is like maybe what, 1 or 2 seconds per pulse, you would get hundreds of pulses in that time. And you would pick all of those up on a radio telescope, and then you would then move on with your data analysis. Okay, so we can use these ultra stable, we can use these millisecond pulsars because they're so stable. And so you can use them as clocks. So you expect, a clock to tick, 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 tick. But if you have gravitational waves, that's going to change the space in between you and the pulsar. So you have the radio telescope on the right here, and you have the pulsar on the left. And so you have ticks, regular ticks on the top, but that's not real life. Okay, so if you have gravitational waves in between those, you have this middle plot here, or the middle line, and you can see that some of those pulses are either delayed, or they arrive a little bit early to your radio telescope. So, but it turns out that we can fit for this. If we know that they're gravitational waves, we can fit for that, and you would get something like on the bottom, right? So you're back to knowing exactly when every pulse happens. And it turns out that we can find the spin period of some of these millisecond pulsars extremely accurately. And so that's, you see this one is, I think it's 2 times 10 to the negative. So there are 15 zeros there. It's very accurate. However, we do need to be very patient while doing this experiment. So we knew going into this that we would probably not detect anything for the first decade, but now we're starting to see evidence for something that's very interesting. And so over 15 years, we have built up our pulsar array, and we've added more pulsars progressively as time has gone on. Okay, so we're not looking, so it would be lovely to have a single black hole detection, black hole binary detection, and so it would be 2 supermassive black holes orbiting each other in a galaxy which has merged with another galaxy. So you have a single galaxy with 2 supermassive black holes, like I said earlier. But the problem is that there are actually many of these things. So if you see one, you expect to have many. And so if you look at something like the JWST deep field image here, each one of those dots is a galaxy. So we have many, many, many galaxies, and probably many of them have supermassive black holes in them. And if they merge with another galaxy, then you have a binary that can emit gravitational waves at some point in its life. And so now it's not like a single drop on the water, a single disturbance. Now it's like a thunderstorm. You have many, many supermassive black hole binaries all emitting at the same time, and you have a hard time resolving any single one of them. And so you have actually a background or a symphony of black holes or of black hole binary systems. Okay, so we now have the 3 big players on the table. Okay, so we have the sources, which are the supermassive black hole binary systems. We have the messengers, which are the gravitational waves that are emitted by those systems. And we have the detectors, which are the ticking clocks, which are pulsars. which we use to detect them. Okay, so now what we do is we sit here on the Earth and we time many different pulsars, and we use, so we have supermassive black hole binary systems over there, and they're changing the landscape of space-time. And you see that there is this, so some of those lines that are coming from the pulsar are sort of wiggly. If they're not straight, then they're either getting delayed, or the pulses that are coming from them are either getting delayed or they're coming early. Okay, and so in this way, you have pulsars which are in step and out of step, and they're doing a very particular dance, which we look for. Okay, so if we want to say that it's gravitational waves, we need to know that all of the pulsars are either in step or out of step. Okay. And to illustrate this, I would like to make an analogy to a football game where MIT is playing Caltech. Okay, so we've put microphones on each of these sides. Okay, so on the top we have a red microphone for now. I should mention all of the Caltech students are sitting on the Caltech side, and all of the MIT fans are sitting on the MIT side. And so you have this red microphone listening in on the MIT fans, and you have a green and blue microphone listening in on opposite sides of the Caltech side of things. Okay. So before the game starts, we're listening to how loud each of the microphones are. Okay, so on the top you have the MIT side, and so you have just sort of, you know, maybe people are like walking around, talking on their phones. I don't know, maybe they went to get a hot dog or something. And then on the Caltech side, you have sort of a similar situation where you have some people being rowdy. Maybe they should calm down. But then you have people here in the middle who are just not really doing much. And so we say that these different microphones are uncorrelated, okay? And what that means is that they have no relationship. So if you pick one, it's completely unrelated to the other two. Okay, and so we say that those are uncorrelated. Now the game starts, and we're listening to both sides, and MIT scores. All right, so maybe the Caltech side was chanting, and they were making a little bit of noise, but then MIT scores. MIT goes crazy, and Caltech gets real quiet because they're not happy about this, right? So, but the game goes on, and then Caltech scores twice, and both of those times Caltech goes crazy. The Caltech side goes crazy, and MIT is pretty upset about those two scores. Okay, so what we have is that the noise levels here are negatively correlated, okay? And this just means when one goes up, the other one goes down. And then on the other side here, you have when one goes up, when one goes down, the other one goes up, okay? Now, if we continue on with this, they're both on the Caltech side. All of Caltech was excited that they scored. Maybe they didn't scream as loud as the other microphone did, or as the other microphone heard, but they're still what are known as positively correlated because they follow the same trend. So when one goes down, the other one goes down. When one goes up, the other one goes up. Okay. And so this is the dance that we're looking for. With gravitational waves, you see this red line. So you see this red line at 0, and that just stands for no correlation. Okay, so it's like the first game, before the game started. Okay, and so you have no correlation between those things. With gravitational waves, you have this very specific line that showed up just now. And so you'll look for the angle between the pulsars, and you'll see if they're in step or out of step. Okay, so either their pulses are arriving early or they're arriving late, and you're comparing two of them. So they're either both early, if you're, well, let's change the slide, because it'll be easier to show you. Okay, so let's say we pick something on the very left here. Okay, that's above 0, so it's positive. It's positively correlated that we're looking for. So you're picking two pulsars, so two of those white dots on the previous slide, and you're going to say, okay, well, what's the angle between them? And if it's between 0 and about 45, then we say that it's positively correlated, and that means that the two pulsars are in step. their times which their pulses arrive is they're either both delayed or both are arriving early. Okay, so that's the Caltech side, right? So if you take the two microphones on the Caltech side, everybody's cheering at the same time. Okay, so now if you look at the one at 90 degrees, okay, so let's say we have a right angle. It turns out that this is like putting one of the microphones on the MIT side, right? So now you have MIT and Caltech, they're anti-correlated because it's below zero. And so the times that you expect to get are either, so one of the pulsars is going to see it early, one of them is going to see it late, okay? And then finally on the right side here, we have another positive correlation, which is similar to the first one. So if you're from 100 degrees and on, we expect for them to be in step again. So we're looking for this very specific pulsar dance where the pulses are arriving at special times compared to another pulsar. Okay. Now, we say, okay, so the theory predicts this dashed line, and the data, which are the blue bars, is exactly what we get, and it follows that theory line. And so this is the evidence that we see for gravitational waves. Okay, so this is the symphony of supermassive black holes and the clocks doing their correlated dance to help give us evidence for this this detection, or for this event. All right, thank you.
So we'll, as mentioned, we'll take maybe 2 or 3 questions, and then we'll have a quick intermission and turn into our Q&A panel consisting of Aaron and other members of the Nanograv team that made this discovery to answer various different questions that you may have on the topic. And online audience members can ask questions too.
For the gravitational waves, do you notice if there's any difference by the size of the black hole around it, like the pulses it creates? Does that make a difference?
Sorry, can you repeat the question?
Like,
Sorry.
For the gravitational waves, is there a difference of like the pulses that it creates based on like the black holes around it?
Right. So the size of the pulse will stay the same. It's just the difference in when it arrives at the Earth. Sorry, the time at which it arrives at the Earth will change. Yeah.
Where are these pulsars located? Are they in the 2 galaxies that are merging, or are they anywhere in this?
No. So they're all within our own galaxy. They're all about at most, a few kiloparsecs away. So that's about, I guess, like 9,000 to 10,000 light years at most. Yeah.
Does the frequency, excuse me, does the frequency of the gravitational waves change based on the mass and the distance between the merging black holes? And then when they actually merge, before that's completed, is there like a magnification that happens in that moment before the wave stops, or at least is propagated and is no longer present at the location where it propagated from?
Okay, I'm not. I need to think about this. The second one, we should maybe talk about. But the first one, you were saying, yes, the gravitational wave that's emitted definitely does depend on the mass of the black hole. The frequency of the gravitational wave depends on the mass of the black hole and the distance at which it's separated. Yes.
So as they get closer,
they go up in frequency. But
okay,
we don't see that. So in nanograv, we typically see black holes which are in the nanohertz regime, which means that these are like the biggest black holes in the universe, right? So like billions of solar masses. And so the problem there is that as they get close to merging, they go out of the nanograv band. So it's actually the in spiral which we're very sensitive to. So like the starting part of merger, of like the full merger process. Yeah. Does that make sense?
Yes.
Okay.
I see there are lots of questions. There's also a bunch of questions online. In order to not make this Q&A super long, we're going to transition to the Q&A panel. So hold on to your questions, and in like 3 minutes, you can ask them. We also have the telescope set up, but it's still pretty bright outside because the sun only set like 30 minutes ago. So essentially for the next hour or so, we'll have both the Q&A panel going on between Aaron and other members of the Nanograv team, as well as the telescopes, and you're free to go back and forth between those two as whatever your will takes you to do. So, but for right now, I'd say maybe wait for a few minutes before going out there because there's not much to see except for the moon because it's still kind of twilight right now. So, okay, so we're gonna set up, but let's thank our speaker again. Excellent presentation. And we'll just set up for, can the panelists come forward and we'll get set up for that? I'm still new to technology. Okay, great. Oh, sure. Okay. All right. We're back after our brief intermission. Thanks for sticking around. So now is the beginning of our Q&A panel consisting of members of the actual Nanograv team. The team, yeah, I know. These are the people. Members of the Nanograv team responsible for making the discovery, so thank you guys. What we're going to do is very quickly just pass the microphone to each member of the team to give a short introduction on what sort of science that they work on related to or somewhat unrelated to the Nanograv Consortium. And then we'll start taking, those of you who already had questions or members from the YouTube audience, we'll start addressing your questions, and feel free to ask, whatever about this result or even broader science stuff, physics, astronomy, and we'll do our best to address whatever you've got for us. So go ahead, sir.
Thank you. My name is Joe Lazio. What we're going to do is the first datum or the first data for this experiment were taken in 2005. So in 2005, I was on the staff at the U.S. Naval Research Lab in Washington, D.C. I got a real thrill out of that because when I was a kid, all I wanted to be was a radio astronomer, and my official title was radio astronomer. And I was thinking about and still somewhat dabble in what does the center of the Milky Way galaxy look like in radio waves. And I was also looking at the positions and motions of pulsars as they move across the sky, which actually has some connection to nanograv.
Hey everyone, I'm Karina Haziano, faculty at Caltech. I work on basically gravitational wave astrophysics, so detecting gravitational waves with LIGO that Aaron mentioned, and now nanograv. And I'm slightly younger, so in 2005, I was in high school. I was getting ready for my last year, so preparing for tests. And I knew I wanted to be an astronomer, but I didn't know anything about gravitational waves and general relativity. That came a little bit later. So yeah, many thanks to unnamed radio observer who started taking that data back in 2005.
My name's Sophie Harahan. I'm a graduate student at Caltech, and I work on both nanograv and LIGO data analysis. In 2005, I was 7 years old. I was in second grade, and I was still losing teeth. I was told that I could be anything that I wanted to be, so I was still deciding between a caterpillar and a fire dog.
My name is Pat Myers. I'm a postdoc here at Caltech. I also work on a lot of nanograv data analysis things, and in the past I did a whole lot of LIGO data analysis things. And in 2005, I was a freshman in high school, so mostly obsessed with running a lot and playing the clarinet and trying not to do homework, I think.
Okay, my name is Aaron Johnson. I am a postdoc here at Caltech, and I mostly work on nanograv, for the past couple of months, I mostly worked on nanograv data analysis, but I also do a little bit of next generation, like what's the next ground-based detector after LIGO, and so I work a little bit on data analysis for that. And in 2005, I would have been 14, probably playing lots of video games, and again, I just like Pat, trying not to do homework.
Oh my God, I feel so old. In 2005, I was starting graduate school, living in New York, and I'm Cameron Hummels. I study galaxy evolution, so I don't do any of this business that the discovery was made for, but I was, trying my best in 2005 to figure out what I was going to study, and now it's computational galaxy evolution. So, okay, so we can take questions from the audience. Okay, let's get it started. You guys have a mic here, too.
So for any of you who are involved in the data analysis, how do you take into account both the wavelength of the gravitational wave from the black holes, as well as the distance to that particular pulsar that you're measuring, and how that interacts?
That's a really good question. So it actually turns out that for a lot of these pulsars, we don't know the distance to the pulsars very well. And so actually the thing that's actually correlated, so the thing that causes the pulsars to sort of be in step with one another, that Aaron was talking about, is the effect of the gravitational waves near the Earth, basically. And so the things that really matter are the gravitational waves near the pulsar when it's emitted, and the gravitational waves near the Earth when it arrives. And we don't know a whole lot about what's happening near the pulsar, but we do know a whole lot about what's happening near the Earth. So actually, if you had eagle eyes and you were looking at that plot, there was a 0.5 on that y-axis. 1 would mean that things were perfectly correlated between pulsars, but because we don't know what's happening at the pulsars, the best you can do is predict maybe 50% of a signal of another pulsar, because we only know what's happening around the Earth.
I can ask one quick follow-up. What does that mean in terms of
You could ask and they'll just repeat the question too. But here.
what does that mean for the wavelength of the gravitational waves that you can detect?
Yeah, that's a very good follow-up question. So what it means really is that the wavelengths that you're sensitive to are essentially related to the time at which the time over which you've been observing. So, because these things travel at the speed of light, there's a one-to-one relationship between the wavelength of the waves and the frequency of those waves. So how much time between sort of crests and valleys of the wave. And so really we typically talk about frequencies of the waves, and the frequencies are related to, the frequencies we can detect are roughly related to how much time we've been observing.
Which, just to put some let's put some numbers on it. So the data are typically taken sort of once every 2 weeks to once every 4 weeks. And then the data set is 15 years. So that means we're kind of sensitive to periods, waves with periods of about a decade. And that's a nanohertz corresponds to sort of 1/30 years.
Well, for example, the distance to the pulsar, we don't really know what it is, but it is much longer than this wavelength. So between us and the pulsar, you have many, many wavelengths that are traveling around the space between us. So the pulsars are it's still within the galaxy, but further away.
Thanks for the interesting talk. I'm wondering why, for comparing the theory to measured values of the correlation over angle, why is there the positively correlated values were a lot higher than the negatively correlated ones, which were pretty close to 0? Is there a specific reason?
Yeah, so that's a prediction of general relativity. So this is what comes out of the equations. And in general relativity, gravitational waves have a very specific geometric structure that goes into those equations. So this up and down and up comes from the structure of gravitational waves in general relativity. The reason it's not completely symmetric has to do with exactly, again, how gravitational waves behave. But basically what that means, if you are observing a specific direction, you have a pulsar over there, and right behind the pulsar, there's a black hole. Well, in the same direction, the black hole is going to be very far away, but it's right behind the pulsar. This is when you get the strongest signal. So basically the strongest delay of the pulse or the weakest delay of the pulse. Well, if you do the opposite, rather than look in this direction, look 180 degrees in the other direction, you get a slightly smaller response. This is what gives you this sort of asymmetry between positive and negative. It's kind of the geometry of how gravitational waves behave that gives you this asymmetry.
Actually, can I ask for clarification? I think, were you asking the data themselves, I think, are not as much negative as the positive?
Yeah, so I was asking about the theory and the data, and the data fit the theory equation reasonably well. So I guess I was curious about both.
Do one of you want to say anything about the data?
Yeah, the fact that the data are not as negative comes from, this is what we expect. The theory says that they are not going to be as negative because of sort of the geometrical structure of the signal. Yeah.
Thanks.
Mm-hmm.
Okay. And YouTube audience, we will get to your questions in just a moment. There have been a lot in person.
So when black holes meet, do they just merge together without turbulence, or is there some kind of big or something?
Excellent questions.
Yeah, so it depends on the angle at which they're meeting. So if they were meeting exactly head on, they'd kind of just fall into each other. But if they're missing just by a small angle, what they'll do is they'll start to orbit around each other. If it's a really small angle, instead of being a perfect circle, that'll look like a very long oval. And when they're very close together is when they'll emit a lot of energy and they'll get even closer.
Does a black hole consume itself? Is that?
Sorry, can you repeat?
Does a black hole consume itself? I mean, when because it's consuming another black hole, is it something that would happen? Would it consume itself?
So when two black holes merge, the mass of the what's called a remnant, which is the black hole that's left over afterwards, is smaller than just the sum of the two black holes. And so like when they're orbiting each other, they're emitting energy. And so that because E equals mc squared, energy is like the same as mass. And so they're actually radiating mass away as well, in a way, if that answers your question. So I guess in that way, they are kind of consuming themselves.
So yeah, I mean, I think there's somewhat, if I may, there's somewhat of a misconception about what black holes are, based mostly on popular media representations of them. Everyone thinks of them as vacuum cleaners that are sucking everything up and consuming everything around them. It's not really accurate. For the most part, unless you're really close to a black hole, it behaves much like any other massive body, like a star, like a planet, like a galaxy, in that it has a gravitational effect on its environment. And things will orbit around it or they'll fall into it. But really, the comparison I like to make is if you were to replace our sun with an equivalent mass black hole, nothing would really change that much in the solar system except it would get dark because the black hole's not emitting light like our sun is. But we would continue to orbit on our normal orbit around that object, which is now a black hole. And so the idea that, sure, when two stars get close enough together, they merge, and that was a very apt question. Is there like when two stars merge, there's probably some sort of electromagnetic counterpart, like an explosion of some sort. But when black holes merge, there's this gravitational wave component that you want to add in. I can tell.
Yeah, so it's this explosion picture that you have in your mind, this violent collision. Actually, this process is a lot more peaceful when you kind of look at simulations and look at, plot black holes. It's actually quite interesting because the black holes kind of come together, and the black holes are defined by basically what we call an event horizon. Think of it like an exclusion region. You can't go beyond that, because if you go beyond that, you're gone. You're never coming back. So these sort of exclusion regions are coming closer and closer together. And at some point, they're so close together that they basically peacefully join. They join together, and instead of two, you now have one, and they come together. So there's no big explosion, because as Aaron was saying, an explosion is, when energy and debris and anything else comes out of some region, but nothing can come out of black holes. So if anything, it's sort of a peaceful process, and anything that could resemble an explosion or anything like that just falls into the black holes. So it's almost kind of funny when you look at those nice animations that like Aaron was showing, it almost looks like a peaceful process. It's just, they come together, they join, that's it.
Yes. You've been waiting a while. So.
Sorry, thank you very much for your talk. I really enjoyed it. I have a question that maybe is not a good question, but maybe I'm curious. So you're working with a distribution of pulsars around the Earth, and you know where they are in angular terms. And so I'm curious whether it's possible for you to learn whether the supermassive black holes that are merging are isotropically distributed uniformly or not. Is that something you can learn?
That's an excellent question. Yeah. We've written papers about it, so maybe someone else want to take it? You want?
Sure. The answer is yes. We can definitely search for what's known as anisotropy. So this would be any deviation from, so isotropy is the absence of any lumps, right? So we do searches like this. So actually the most recent one came out with our set of papers the other day. Well, okay, so it's not published, I guess, yet, but yeah, it's available. You can look at it online if you're so inclined. But yes, so at the moment we do not detect any significant areas of anisotropy. So we do see maybe, but it's not statistically significant. So yeah, there's not really anything there at the moment. Yeah.
Yeah, and you'll hear people say that we think it's supermassive black holes, but we can't say it's that versus some other model for physics, and anisotropies, so having hotspots on the sky, which would probably be dominated by like individual systems or clusters of individual systems, would be sort of a telltale sign that this signal would be from supermassive black holes, because most other theories predict something that is uniform across the sky. Yeah.
So LIGO can figure out the masses of the black holes that are merging, right? So are you able to tease out the different frequencies? Because it's a thunderstorm, you said. So are you able to tease out the different frequencies and amplitudes and tell us, like, what is merging? What are the things that are merging?
Yeah, so that's a really good question. So what we have evidence for is this sort of thunderstorm of gravitational waves from lots of systems together. And the sort of overall size of that background combined with essentially the size of the gravitational waves we see at one period versus the size at another period, and sort of their relationship with one another. So whether you have, more gravitational waves at faster periods versus sort of slower periods, that'll tell you about the different populations of black holes that are merging out in the universe. And so what you do is you build up a theoretical model for how these black holes form over the history of the universe. And there are different sort of dials that tell you how many you get and things like that in your theory. And those different dials correspond to different sort of heights and different relationships between how much gravitational waves you get at one period versus another. And so there is, similar to the anisotropy question, there is a paper that talks about this, and you can actually get some idea of, at a given frequency, how many black holes of a given mass would you need to produce the signal that we see. And you also have to say something about, where they occur in the universe and that sort of thing as well.
Yeah, so most of them are black holes that have 10 to the 9th times heavier to the mass of the sun. So that means, 1 billion times the mass of the sun, orbiting around another black hole of basically around the same mass. And let's see, most of them are kind of relatively nearby in the galaxy. Nearby in astronomical terms is still very far away. It's hundreds and hundreds of megaparsecs. Does anyone remember what that's in light years?
Times 3.
Millions of light years away. There's so many units in astronomy, it's very hard to remember. Lots of numbers. But this is what we're talking, that's what we're talking about, like supermassive black holes. These are black holes 1 billion times more massive than our sun.
So there were a number of questions from our online audience, and I wanted to get to a few before there's a mutiny here. One was, so you talked about making these discoveries from outside of our solar system. These gravitational waves are coming from these distant supermassive black holes that are merging, but how much do we need to know about the mass distribution around us from the solar system, the position of the sun, the position of Jupiter, and how much does that influence our detection of these and mask perhaps some of their behavior? How much do we need to know about that?
A fair amount. So technically when, as Aaron was saying, what we're doing is measuring essentially the ticks from these pulsars. If you stop and think about it, well, the Earth, the radio telescopes we use around the surface of the Earth, and the Earth is rotating, it's moving around the sun. So what we actually try to do is not measure them, well, we try to transform or we try to correct for when we would have measured it if we were sitting at the center of mass of the solar system. So the center of mass is, if you can imagine, what's that point in space, and all of the mass is it's sort of the balancing point of the solar system. That's just outside, it's typically just outside the surface of the sun, because it is determined by where all the planets are relative to the sun in the course of their orbits. So we have to correct for that, or we try to correct for that and say, what is the time each pulse would have arrived at the center of mass of the solar system? That means you need to know the masses and the orbits of the planets in the solar system. And the most important are Jupiter, Saturn, Uranus, and Neptune, because they're the most massive. And it actually turned out we in the collaboration probably spent a year trying to make that correct, trying to make sure we understood how to do that correction when we were back at sort of the 12-year data set, because the orbit of Jupiter is like 11 or 12 years. And so there's a real risk that we could have gotten it wrong if we didn't have the orbit of Jupiter quite right. And I actually didn't say it, I'm on the staff up at JPL. So NASA's Juno mission, which is currently orbiting Jupiter, has been one of the key pieces, one of the key measurements that we've used to try to help make this correction. And looking toward the future, as we get more data about the outer solar system, that will help us in improving where is the center of mass of the solar system, which we actually need to know to something like the scale of a football field.
In other words, a few years ago, we didn't have these corrections, and we managed to detect Jupiter, and maybe a few centuries later than everyone else. And then we put Jupiter on the right side in our equations, and the signal went away.
There was an additional question. Oh, I'm sorry. Forgive me.
I just wanted to mention that, so what those are called are ephemeris, which is basically where all of the planets are. And when your astrology app, say, fetching NASA data, it's the same files. And so if you have CoStar, anyway, add me on CoStar.
So there was a question, is it conceivable to think that any of the gravitational waves that were detected could be as old as the inflationary period of the Big Bang, the very early universe? Or are these gravitational waves coming from reasonably nearby supermassive merging black holes?
Yeah, so that is one of the possible interpretations, and there are models from the early universe that predict gravitational waves with the spectrum that we see. It's a little bit less likely, I think, than supermassive black holes, because you can look out at the number of galaxies that we can see, and you can make predictions for roughly how big you expect the background to be from supermassive black holes. Whereas a lot of these models from the early universe, you get constraints at sort of very, very, very long wavelengths of gravitational waves using radio telescopes that observe sort of the afterglow of the Big Bang. And then between them and where we're making a measurement in frequency space, there's a lot of unconstrained stuff going on. And what happens in between the Big Bang and now is pretty uncertain. And so there are models, and they do fit the data. And this is, most of those models, as someone asked earlier, most of those models predict a purely isotropic background, whereas these supermassive black holes would predict something that looks a little bit lumpier on the sky once we have enough sensitivity to detect that. And so that's really when we'll know what this background actually is coming from. Is it these supermassive black holes? Is it something from the early universe? Is once we can detect or not detect these anisotropies. And after a certain point, you should be able to detect, hot spots on the sky to some level that you can model theoretically. And so that's sort of how you would distinguish between these two models eventually.
Okay, and that's related to another question. Can you disentangle the principal major component of the detective waves to isolate it to like a nearby system? So not right now, but potentially in the future with more signal?
Yeah, and I should say we also do search for individual systems as well that are emitting gravitational waves. And those look like, on their own, they look basically just like sine waves in the data. And so That's something that we search for, but at the moment, what we have evidence for is this sort of collection of all of them. And then what will hopefully happen soon, in the next several years, would be great, is that we'll see sort of an individual sine wave from an individual system.
Do you have any predictions on the increased, like the necessary increase in the technology or the number of pulsars that you'll have to be monitoring or the sensitivity of the instruments before you'll potentially be able to make a detection like that? Is this like a decade? Is this a century?
I think the timescale is decade or so.
Okay.
Yeah, that's absolutely true.
Okay.
Yeah, so there are some papers that suggest, based on realistic simulations, that with 20 years of data, we would have maybe a 40% chance of having something that is emitting loud enough for us to see. But that's a very uncertain prediction because we don't know how many pulsars will time and how frequently and things like that.
Okay.
So.
Sorry, I've been hogging the questions with the online audience. Additional questions here? Yeah.
So I have two questions. First, you said you don't know the distance to the pulsars that you use for the timing arrays. I thought those were standard candles, but I guess if that's not true and you don't know the distance, if you could figure out the distance, would that additional information be valuable for your? And then just explain what that would add. And then the second question is just, you talked about having to know the center of the mass of the solar system. How do you account for undiscovered objects like, say Planet 9? Is it just that it's because it's theorized to be somewhat massive relative to the other planets, but is it just not massive enough to matter in terms of that football field?
Yeah, so it would be really a dream come true if we actually knew the distances to the pulsars very well. And there's some data that can use recent data to maybe get them to a little bit of better precision, but it's actually quite difficult. So what you need to do, ideally, you need to get them to figure out what the distance to the pulsar are to within a wavelength of the gravitational wave. So to within, one of those waves of the gravitational wave, so you know exactly which of these oscillations the pulsar is in. And since you have so many waves between us and the pulsar, you need to get it to pretty good precision, which unfortunately is very difficult. As I think Aaron and Pat were saying, we're basically, because we don't know the distance to the pulsar, we're leaving a lot on the table. We're leaving a big part of the signal. We cannot use it. So if you had an individual source, which is one of the big goals for the next years, if you knew the distance to the pulsar, you'd basically be able to recover the rest of the 50% of the signal that we're currently essentially cannot use at all. So it is one of the big dreams. If we could get with other data, astrometric data, understand the distance to the pulsars better, we would really unlock essentially 50% more signal. So yeah, that would be very, very important. And the question is about Planet 9.
Yeah, so it's a combination of Planet 9 is very far away. Typically, sorry, yes, good point. If there is a Planet 9, the distance to it would be it's substantial. I think the estimates are like 700 times the typical Earth-Sun distance, and for scale, Jupiter's kind of like 5. And then on top of that, it's not, it's predicted to be sort of Neptune mass, I think. And the other really important thing is its orbit would be, if it exists, the orbit would be very long. So on the time scale of 10 years or on the time scale of 20 years, it almost doesn't move. And in that sense, it doesn't affect the center of mass. And if I can just expand on, so how would we do these distances to pulsars? And the classic thing is, if you put your finger at a distance and then close one eye and flip back and forth between eyes, that's an effect called parallax. And what we'd really like to be able to do for all these pulsars is make a measurement of them on one side of the Earth's orbit and then on the other side of the Earth's orbit. And the challenge is, one, pulsars tend to be very faint, and we don't quite have the telescopes that are sensitive enough to detect all of them. And then on top of them, as they move farther out into the galaxy, if you just do it with your finger, you'll see that as you move your finger away, it starts moving less and less relative to the background. And as they get farther away, it becomes just that much more challenging of a measurement to actually make. And so that's the limit. That's one of those limiting factors of how well can we actually make that measurement. And it's a challenging one to make at the precision that Katarina was saying.
And there aren't other like standard candles that you could use to ladder your way to where they are, just because they're so faint, or
Not to the precision that she was.
okay.
Yeah. Oh, you have a question?
What makes black holes like so dark?
Excellent question. It's so when you see something with your eyes, what happens? People for a long time didn't know what would do that. So there were ideas. Maybe our eyes, shoot out things and observe stuff, or maybe something comes from the object to our eyes. And it turns out the second is correct. What happens is you have light everywhere around you, and light bounces around, and eventually at some point, light randomly reaches your eye. And if some light has bounced here and then comes to your eye, that's how you see. So in order to see black holes, you need light to go to the black hole and then leave from the black hole and come to your eye. But that is impossible. Black holes do not let anything escape. So because they don't let anything escape, nothing reaches our eyes from them. So that's why they're black. We don't see anything there.
Thanks for answering so many questions. I'm just wondering, what are fundamental particles in those supermassive black holes? Because I was thinking Dr. Johnson mentioned like pressing Earth to a coin, and I was thinking all those atomic structures will be destroyed. Do electrons still exist? And I'm asking that because I was wondering, when they merge, do those fundamental particles change? And then you say you do computations and simulations. How do you treat them and those kind of stuff?
Yeah.
So we also mentioned that neutron stars were the most stable matter that exists. So it's a little misleading to call what's behind a black hole's event horizon matter, because the way that we understand matter is that it interacts via like light hitting other things. But when you're inside of a space where light can't really move around, that kind of becomes less of an actual notion that you can have. So inside of simulations, when you ask what happens inside of the black hole, what happens inside of the black hole is you cut it out of the simulation and you just talk about what happens at the edge of the black hole, because that's what we can observe. There's no way to observe the inside of a black hole directly, because again, how do we observe things? We shoot light at it and it comes back. But when you shoot light at a black hole, it doesn't come back.
And if you don't like this sort of, observational approach to things, which is what we astronomers do, and, you want to actually understand what happens inside the black holes, even if you have no chance, as Sophie said, of observing it, the answer is we don't know. Our equations, Einstein's equations of general relativity, essentially break down when you get to the centers of black holes. So we don't really understand what happens at those, or whether there could be any form of matter, what forms it would take. But this is a question that astronomers, we have very conveniently hidden it inside a horizon and said it's hidden. We'll never get any information about it, and will never affect our universe around us. That doesn't mean that there is interest in this question. There are a lot of people trying to understand what happens, but it gets to the edge of it gets to interesting questions of what is actually knowable. Because if there is no chance that anything will ever, any information about something will ever come to you, I don't know, does it even exist? The whole tree in the forest question.
So go ahead, please.
I did want to actually ask, and I want to ask Katarina a follow-up question, which is, so you asked about black holes, but we also mentioned neutron stars, which are astonishingly dense things that compress a lot of matter into a very small amount of space. And what happens when you compress a lot of matter into a very small amount of space is something that Katerina is an expert in, and is like a wildly interesting question that a lot of people are interested in. So what happens in the center of a neutron star?
It's another question, the answer to which I don't know. But a lot of people are very interested, but because it is knowable, there are a lot of people who've spent decades trying to understand it, both theoretically by doing calculations and observing neutron stars, like the neutron stars that Aaron talked about. So what happens inside neutron stars, as far as we understand, is that matter becomes so dense that eventually you start losing the notion of the different constituents of matter that we know every day in our everyday lives. So typically we have molecules, and then molecules inside molecules we have atoms, and then atoms are mostly a nucleus of protons and neutrons with electrons around it. So you squish matter so much, so closely, tightly together that, first of all, you can't have molecules. They're so close together. You can't have atoms. They're so close together. You get to the point where you don't even have nuclei, because rather than a nucleus and electrons around it, you have a nucleus one right after the other. So you don't know when one starts and the other ends. And then you continue packing things even more and more densely, and you start not being able to tell protons apart. All the protons are one soup together. You squish things even more tightly, and you break the protons apart into their constituents, which is quarks. And you can't even tell the quarks apart. And at that point, really everything, our knowledge really breaks down. But these are questions that the answer to which is knowable, and there are a lot of scientists interested in those questions. So we have, there's okay, and then in the center,
I was just wondering, how important is quantum computing to this field?
Something for the data analysts, maybe?
We'll get there.
Yes, so unfortunately at the moment, we don't have a quantum computer that can handle, it doesn't have enough. So computers work on bits, quantum computers work on qubits, and we just don't have enough qubits to have a stable computation, meaning that we can trust the output of that computation. And also we don't have the algorithms that we could use to really do the computation in the first place. So there's probably a long time before we get there, unfortunately.
And the thing I'd add to that too is that generally traditional computers based on CPUs, central processing units, oftentimes the code that's run on those types of machines is very different than the kind of problems you'd want to test with a quantum computer. So they're almost, it's not just like quantum computing is the next thing and it's going to solve all the things that we haven't been able to do in lack of efficiency in our own traditional computers. It almost like it tackles different kinds of problems. So they really are going to be complementary to each other in dealing with different aspects of problems. But certainly there are a lot of things that quantum computers that will be able to do that we can't currently do with traditional CPU.
But can I add one more thing?
Yeah.
Not exactly on computing, but one of my favorite facts about gravitational wave astronomy, what we do. You hear a lot about the vast amounts of data that are being produced everywhere, and of course also sciences. You hear about how much data CERN produces to the point you can't store all of it, you have to delete at some point. The Event Horizon Telescope couldn't transfer wirelessly the data from telescope to telescope. They literally had to take hard drives and physically bring them from location to location because there's so much data. Gravitational waves are not like that at all. Because our frequencies are so low, it means we don't produce as much data. So LIGO observed black hole binaries, and in the previous sort of observing campaign that was the detectors were on observing, it found something like 50 black hole binaries. The entire data set that contained that was about 1 terabyte. It can fit in pretty good thumb drive. We don't produce as much data as other fields, but that data is really packed with science. So, question.
So, if the black hole disappears, will it affect Earth or no?
If you think of like the sun being turned into a black hole and then that black hole disappears, something like that?
I mean, like if just the black hole disappears with no reason, will it affect the Earth?
Mm-hmm. Yeah, so depends on which black hole it is. There are a lot of black holes in the universe and a lot of black holes in the galaxy. So there's something like 1 billion black holes in the galaxy just floating around. The most important of which is at the center of the galaxy. We have a really big black hole, about 1 million times the mass of the sun. So if that disappeared, the first thing that we would notice is that we're constantly observing what happens at the center of the galaxy, and we would see things really going wrong in the center of the galaxy. Fortunately, we know of no black hole that's close enough to Earth to really affect us directly. So we would not feel, that black hole disappearing for a long time, but a lot of astronomers will be very confused if that happens.
Any other questions from the in-person audience? Yeah.
So before we had the technology to detect gravitational waves, how did Einstein know that they were likely out there?
Can you repeat the question?
Before we had the technology to detect gravitational waves, how did Einstein first theorize or know that they were out there?
Initially it was the math. It was that if you have these small perturbations in space-time, then they're gonna travel like waves across the universe. So it was really the math. I don't remember the history very well, but
yeah. So Einstein proposed general relativity in 1915. And he did the calculation for gravitational waves just 2 years later, in 1917. His original calculation had a factor of 2 error. So, happens to all of us. And even perhaps slightly more embarrassing, it took the field almost 40 years to convince yourself that they're actually real. It took a very long time to understand the math well enough to convince ourselves that they are real and not just some sort of artifact that comes out of the equations. Even more embarrassingly, Einstein himself was never convinced. He changed his mind. He tried to argue that they were not real. He tried to publish a number of papers arguing that they're not real. Unfortunately, he passed away before the final mathematical proof that they are real. So he didn't see that. And he obviously didn't see the detection because that was 100 years later. So it's a very long process, a very interesting story, both from like a theoretical perspective for scientists to convince themselves that this is something real and worth looking for. And then after they convince themselves it's worth looking for, to actually get to the technology level, like you mentioned, of actually doing it.
And there are a number of other interesting aspects to this entire story along that line of, for instance, neutron stars were more or less hypothesized or theorized sort of in the 30s. But if you did the very simple calculation at the time, using the physics known at the time, they would have been way too dim to detect. And it turned out that we didn't understand all the physics at the time. And so they were discovered completely accidentally by a graduate student who was trying to do something completely differently. And even, my sense of the history is that actually another graduate student then discovered 2 neutron stars orbiting each other. And it became clear that their orbit was shrinking. And the only thing that could explain that was the gravitational waves being emitted, that the 2 were losing energy. And that was really one of the key things that helped get LIGO started, because then you could really point to something and say, we're sure that it's losing energy due to gravitational waves. And so it makes sense to actually build a detector to go look for more.
There's one question from the audience that I wanted to get to. What's the advantage to observing black hole neutron star mergers over black hole mergers to detect gravitational waves, which is giving more efficient results for the gravitational field like LIGO, or potentially for this? I guess you can't have supermassive neutron stars in the same way that you can have supermassive black holes, but can you talk at all about that?
Yeah. So we have detected what happens when 2 black holes merge. We have seen neutron stars in binaries since basically the 70s. We've also seen them with LIGO. But interestingly, we had never seen a neutron star around a black hole. And there's no inherent reason for this. The neutron star could emit, if it's a pulsar, it can emit pulses. We could have detected it. And it was one of the sort of holy grails of astronomy to try to find such an object. And a lot of effort to find them. And eventually astronomers searching for them with light could not find them, have not found them to this day, but we have found them with gravitational waves. So LIGO has detected about four of those mergers of a neutron star and a black hole to date. So compared to, for example, 60, 70 systems of two black holes merging, the neutron star black hole ones are more rare, but they're a lot more spectacular. First of all, because it's a completely new type of system that we knew should be out there, but for some reason astronomers could not find it, and now we have finally found it. The other interesting thing is that because black holes are, well, like we're saying, black, they don't emit any light, you can't see them, we can only observe them with gravitational waves. When a neutron star is involved, there's actual matter emits light, so you can also observe it with light. So this is the big advantage. When a neutron star is involved, it also opens up this huge other possibility of not just observing with gravitational waves, but also observing with the traditional light that we're typically using to look at stuff. So that's the big advantage of pairs of neutron stars and black holes together.
Before we keep going with questions, because we both have in person as well as online, I just wanted to mention the stargazing is only going to go for about 25 more minutes. So if you wanted to have an opportunity to look through the telescopes sometime in the next 20 or so minutes, I'd encourage you to zip on out there and check things out. But that's not a means to dissuade you from sticking around, because we've got some great information from the panel, and we have a question right here.
Thank you. I want to ask, since for the lectures I learned that black holes are like observing all the energies into it. So I want to ask, will the black holes losing its energy, or it's like continuously just growing? What's the end? I'm just curious.
Excellent question. Oh yeah. The question is, we said how light cannot escape black hole, so the black hole keeps absorbing things. So what happens as it keeps absorbing stuff? Does it just grow forever, or does it ever lose any energy? And goes back a little bit to what Sophie was saying. We're getting to the edge of stuff that we don't really know. Not completely unknowable. This is another question that is under a lot of debate, a lot of theoretical debate. So if stuff falls into the black hole, it means we completely lose them. We never hear from that ever again. And that is typically something that is a little bit unsettling, the completely loss of something. So there are some ideas, and maybe the stuff doesn't completely fall into the black hole, but maybe there's some energy that's hovering right outside the horizon of the black hole that maybe can escape and leave towards infinity. So maybe black holes are not completely black, but they emit a little bit from outside the horizons. So that is called Hawking radiation. And if you follow this kind of line of reasoning, you basically end up with black holes not really being black, but they actually evaporate. There was a question, what happens if black holes disappear? That's a way that black holes could disappear. So especially very small black holes would completely evaporate this way by just losing all their energy. This is not a process that is 100% understood, but there are a lot of people, again, trying to understand it both theoretically and trying to see whether there can be any experimental evidence. It's hard to figure out how to do this observationally because we don't have any black holes close by, probably, thankfully. But there are people trying to build systems that are more analogs to black holes. So systems that are on Earth here that you can kind of manipulate and say they kind of have some of the same properties as black holes. So maybe we can use them to understand things. These are called black hole analogs for obvious reasons. But again, this is a big question. We don't really know. But for the kind of big black holes we're talking about, even if they are losing energy, it is so slow that the time scale, the time it takes for them to evaporate will be longer than the age of the universe. But any small black holes, very small ones, would basically evaporate almost very fast, almost immediately. Mm-hmm.
So I could be wrong, but I've heard that due to Hawking radiation, a black hole reaches a certain threshold where it's lost enough of its mass that it can no longer contain the mass that it's consumed throughout its lifetime, and it all kind of just expands outwards, kind of just explodes out. So I'm wondering, are there any theories as to what form that matter takes once it is released?
Not really. So, these are the kind of hard questions. The problem is that there's no sort of one sort of self-consistent theory that you can rely on. You have to collect ideas from different theories. General relativity itself, says, I don't care, there's an event horizon. I don't care what happens inside of it, like Sophie was saying. But if that answer is not good enough, and we have reasons to think it's not good enough, you have to start sort of patching it with other ideas from other theories. And there's no sort of one unified framework in which you can do this. Again, these are sort of some of the big theoretical questions. But yeah, it takes a lot of effort from a lot of people over many years to try to put together all those concepts and get to a satisfying answer.
So there was a question from our online audience asking about gravitational waves traveling at the speed of light, but different parts of the universe are potentially expanding faster than the speed of light. So how are we able to measure the gravitational waves coming from regions where this expansion might exceed that travel?
I'd say, just as Katerina or Pat said already, in cosmic terms, these are relatively nearby binary systems, so only hundreds of millions of light years away. And on that scale, we don't have to worry about the more larger general relativity and the aspects of it expanding way faster than light.
Okay. I personally had a question which maybe was discussed, maybe it was in the suite of papers that was released, but do we have any insight to the number of binary systems that make up the signal that was detected in this publication? Like, is this 100 supermassive black hole merger like binaries, or is it a million? What's the kind of idea that we have?
Yeah, so the number that I remember from the paper that I quoted yesterday in my talk actually was that for, I think, the lowest frequencies at which we're looking, it's something like of order 100,000 binaries that are contributing to it. I think that's what the modeling would suggest.
Okay.
And then as you get to higher and higher frequencies, it becomes significantly less than that, because we see a much louder signal at lower frequencies or longer periods.
I see.
And then you also see heavier masses contributing at lower frequencies as well.
Is it because the higher frequencies are farther into the in spiral, and the supermassive black holes themselves are so large in their event horizon that they get too close together and they just merge and they wouldn't have that signal at higher frequencies? Is that the reason, or is it some other?
I think it's that as you get to higher and higher frequencies, they spend less time at an individual frequency. So if you think about like the LIGO chirp, for example, towards the end of its life, it's moving really quickly up through the frequency band. So that's what that chirp looks like. And these things are doing a chirp, but just on a much, much longer time scale.
Sure. But they populate that part of the frequency band for a much less time.
Exactly.
I see.
Yeah.
Okay.
That's right.
Sorry. I had to take, yeah.
Thanks. Okay. This may have been answered earlier and I didn't pick up on it, but I gather from what you've been saying that black holes can only come into being inside of a galaxy. Is that correct? They can't form outside of a galaxy. And if one can form in a galaxy, then more can form. And if there are more, eventually, two of them will get close enough together that they will combine. So I can see in the future that more and more black holes will be created in a galaxy and eventually wind up consuming the galaxy. My final question, is there a limit to the size of a black hole? We know that stars can only exist for so long and then they disappear. Is there any problem with black holes growing as much as there's food to feed on.
So I can go ahead.
So I guess it's inside of our galaxy, there's like a supermassive black hole, and LIGO has detected other black holes in different galaxies. And I think it is true that you can have these what we'd call like hierarchical mergers. So like a very massive star explodes, becomes a black hole. So that would be like a stellar mass black hole. So like 30 stellar masses. And then those can merge and then they can make more and more. But once you start getting to situations where you need more and more black holes to merge into each other to create a larger thing, it becomes less and less likely that that has happened. And so, yeah, but I don't know much about the formation of supermassive black holes.
You said less likely, but that's just a question of time. Eventually it's going to happen. Right?
No. I think Aaron may have made reference to this, that, I don't know, are they going to be able to see M31, the Andromeda galaxy?
No, M31, okay. No. Sadly.
So the nearest big galaxy is the Andromeda galaxy. It's a little bit larger than the Milky Way. And I think Aaron made the comment that, in fact, the Milky Way and the Andromeda galaxy are falling together. And yeah, it's like 4 billion. Yeah. When that happens, yeah, go update. No, keep paying your life insurance. When that happens, most of the stars, in fact, there will be almost no stellar collisions. It will not be the stars that collide. And space is really, really big, and stars are small, and any black holes are actually smaller. So typically, and in fact, all of the action in the figure that Aaron was showing was really the clouds of gas that are in the galaxies, and they do interact. But when you get to stars, they're so small and the space is so big. In general, you can assume that almost none of the stars will ever collide when the galaxies merge. They will never collide.
On the question of how big they can get, I don't remember if anyone has a better recollection of the number, but I think the record holder heaviest, most massive black hole that has been found is something like 10 billion times the mass of the sun. The ones we're talking about here are 10 times smaller, so 1 billion times the mass of the sun. But this is sort of the record holder that has been found.
I'm interested in exotic matter, negative mass, negative energy, and how that relates to like M theory, string theory, the idea that size can change but shape doesn't. And I wonder how that relates to black holes, if you've looked at that at all.
Yeah, so within the sort of the way we study black holes is typically within general relativity, and the observations that we are taking of black holes, of neutron stars, they can all be explained this way within general relativity. That being said, there are a lot of other observations that cannot be explained as neatly. For example, dark energy and dark matter, or this is where the whole idea of quantum gravity and what happens in the course of this central singularities of black holes comes about. So when you go into this regime where general relativity can no longer explain exactly how the universe behaves, is when you have to start, or either observationally or theoretically, it's not a completely satisfying answer. That's where you are starting to consider things like what you mentioned. But when it comes to the astrophysics of these black holes, they can fully be explained by general relativity. So those kind of those phenomena do not directly come into play. That being said, there is one aspect where dark matter comes into play, because we're talking about galaxies and galaxies merging, and galaxies have a lot of dark matter. This is how we originally realized that there's something weird going on. So when two galaxies merge, the dark matter around them does play a big role in this process. But then by the time that our observations, start coming into play is many, many years after that, when the galaxies have settled down, and it's at the black holes at the center that we're observing. What happens during the galaxy merger? During that time, the black holes are very far apart. They're not really interacting. We can't observe them with gravitational waves. There are other efforts to understand what happens when galaxies merge, but what we're doing here is many, many years after the galaxies have merged and after the dark matter around the galaxies has interacted.
So there's a supermassive black hole at the center of the Milky Way. There are supermassive black holes at the center of other galaxies that we've observed, but there are also some galaxies where we don't see black holes at the center of them, right?
We don't directly observe them in the sense that we can't, pinpoint the effect of that particular black hole, but we think that most of them have some sort of big black hole at the center.
Okay,
but it's not like in our own galaxy we can directly, pinpoint what happens at the center.
What I'm trying to get at is my understanding is that most, but not necessarily all galaxies have. But even if it is all, even if there's a supermassive black hole at the center of all galaxies, it's the dark matter that creates the scaffolding, the structure that forms the galaxy. It's not the black hole at the center. So why do we think that there are supermassive black holes at the center? Because intuitively, it sounds like that must have something to do with why the galaxy is rotating around this object, but it isn't, and it's not as massive as it is. It's not massive enough to have that kind of effect throughout the galaxy. So what is the current understanding of that? Why are they in that location in all these galaxies?
Excellent question. Galaxies are big. A lot of things are happening, and I wonder if that's closer to your.
I'm happy to talk about this. This is my
talk
jam.
for an hour about this.
So.
But that's his expertise. He can answer it better than any of us.
So you're absolutely right that there oftentimes is this misconception, and you have it right, that a lot of people, their perception is based on our solar system. At the center of our solar system, we have the sun, and then we have all the planets orbiting around that sun. And that works because the sun makes up 99.99% of the mass of our entire solar system. So everything, basically any of the other planets don't matter relative to the mass budget, so they orbit around that. But in a galaxy, for instance, our Milky Way galaxy, the supermassive black hole in the center of our galaxy is like a few million solar masses, a few million times the mass of the sun. The galaxy itself is about 1 trillion times the mass of the sun. So that budget is very small compared to all the stars and all the gas and all the dark matter orbiting around that center. So you're right, they are both orbiting around the central point of the galaxy, but it's almost happenstance that supermassive black hole is there. It's not that we're orbiting around it because it's there, it's because it fell to the center of the gravitational potential of the entire system. So essentially, think of it in 2 dimensions where you have the Grand Canyon, right? I love illustrations, even though I'm so bad at them.
You
got like this, and you've got this, and the Grand Canyon, if you have a big massive ball, we'll call it a supermassive black hole, but let's just say it's a big beach ball, and it's going along here, any kind of perturbation, eventually it's going to roll in here and it's not going to come back out. It's going to be stuck in the bottom there, and no amount of pushing is going to bring it out of the Grand Canyon because it has to overcome these gravitational potential walls. It's the same thing in a 3-dimensional sense. Essentially, the gravitational potential, this dip from all the mass of all the dark matter and all the stars and the gas, has this dip. And once something falls into that, it's not going to come back out. So of course, that's the location where something like a supermassive black hole, where a very massive object is going to end up. But it's not that we're orbiting around it per se, it's that it fell to the center of that potential.
And that thing at the center isn't going to affect the size of the walls.
That's right. That's right.
And the fact that we observe supermassive black holes, is that because
other objects fell in and collided? So we don't fully understand the formation mechanisms of these supermassive black holes. I don't know if that was covered at all. I was running around trying to do stuff. But supermassive black holes, these million or billion solar mass black holes, it would take a very, very long time, much longer than the age of the universe, to take stellar mass black holes of 1, 2, 5, 10 solar masses and merge them and merge them and merge them, because that time scale over which those form is much too long for you to do more than like 10 or 20 or 100 of those to get up to these million or billion solar mass. So we don't fully understand, and this is one of the things that's in the news, and a very active field of research is trying to understand how you form these supermassive black holes at very high redshift at the early part of the universe, because it doesn't seem like there's enough time to form those supermassive structures in the very short time that the universe had been around before we start observing them. But even today, it's hard to form them under that time scale, the age of the universe, 13, 14 billion years. So it's definitely an active area of trying to understand how you form these things. But yes, it's no surprise that these massive objects would be in the centers of these systems, because that's the center of the kind of like the trough, the Grand Canyon, the gravitational potential of the galaxy. Yeah. Sorry for stealing the show there for a second, guys.
I had a technical question. You said measurement cadence was every couple of weeks, for instance. When you actually swing the dish around, what's the signal, what's the measurement you make at the feed horn? Aaron showed showed a graph with pulses and what looked like pulse jitter, but I'm guessing that you actually measure a frequency every couple of weeks.
Well, you're actually making, let's see. You're collecting effectively you're collecting, I mean, you said at the feed horn, so you're actually collecting the electric field. The radio waves are bouncing off the big surface there. So in general, the universe is faint, and we're using these big surfaces to collect a lot of radiation and then focus it to the center. So it's not that much different. The way that the radio telescopes are built are not that much different in some sense than, say, the telescopes you might see out there. It's just a different wavelength. And then you're collecting the radiation at a central point. We convert it into an electrical signal, and ultimately, the way the systems work today, that electrical signal is then converted to digital numbers, so-called analog to digital converter. But effectively, you're digitizing the signal. You're converting it to ones and zeros, so you can feed it into a computer. And hit me up afterward. I can go into more of the technical details. But actually, what you're doing is collecting data probably over a course of, say, 15 to 20 minutes, and folding the data at the period of the pulse to build up some signal to noise. And that's what's actually measured. Then that's what goes into the so-called time of arrival that's actually used for the gravitational wave measurement. So you can see me gesticulating wildly. It's easier to draw that, and that's probably a longer offline conversation, but it's collecting the signals, converting them to digital numbers, folding them at that period of the pulsar, and that's then what the data analysis is using. Yeah.
I remember learning that in order to take the first image of a black hole, we needed the size of the size of the telescope needs to be the size of the Earth. And I was wondering if it's possible to point multiple satellites that we have in space at a black hole at the same time, and then put together those images, because basically we can maybe create a telescope that's the size of Earth orbit or even Jupiter's orbit. Would that give us a better image?
Yes.
And why aren't we doing that?
Because it's very expensive.
Oh, okay.
And when you first try to do something, you first prove that it works. And then when you prove that it works and show what spectacular image you can take, that's the next step, where you start thinking along the lines of what you're thinking, how can I make it better? But first you need to prove that it works, right? But there are people who are thinking exactly about what you're saying, how to do this, make you want to talk more about this? Yeah, so there are people who are exploring both, how much better the measurement would be, because you have to know how much better it's going to be. If it's not going to be better, then there's no point in doing it. So you have to know how much better it's going to be. And you have to start thinking exactly where you're going to place the satellites, what specifications they're going to have. So there are people actively working on this. Absolutely.
The comment, sending a satellite to another star is not only expensive, money is against you, but time is against you too. Just to go to another star, to go to the center of the galaxy, it takes 10,000 years.
Yeah, but I mean, as I think the questioner asked, she said even just nearby, to the orbit of Jupiter or something, you could do a lot by just like getting out to the orbit of the moon.
Or even the ones that we already have, out there.
The image of the black hole at the center of M87, the Virgo cluster galaxy that Aaron showed. We don't have any telescopes working at the frequencies that were used for that currently in orbit, or if they are, they typically point down to study the Earth's atmosphere or point at the Earth's atmosphere. So they're kind of pointed in the wrong direction and not working at the frequencies or the colors of light that we need for these kind of measurements.
But they're trying to get money to do this, the EHT
We're trying
consortium.
to figure out exactly what kind of orbits would be needed, what kind of frequencies,
Sure.
and how many you could actually look at.
Okay, cool. Related to that, there was the question, do you build more specialized radio telescopes for pulsar observations of this sort, or just get more time on existing radio telescopes that are already out there?
Yes.
Yes. Okay.
So, yes. Yeah. I mean, actually, I don't think that the study of pulsars has ever motivated by itself the construction of a radio telescope. But it turns out if you can get the radio telescope to work for doing pulsars, it'll work for essentially anything else. So very often, one of the first measurements that is made is show that you can do a pulsar. And it's a great PR thing because you point the telescope in the direction of a pulsar and then you convert it to sound and you get this, so it's a fantastic to show that it actually works. Convert it to sound and you can hear the pulsing of the pulsar and it's like, yep, it works.
But there. Yeah.
The millisecond pulsars actually end up converting to audio pitches. And so actually someone in our collaboration took all of our pulsars and rounded them to the nearest pitch that you'd normally have on a piano and used it to recreate the theme song from Star Trek: The Next Generation. Very funny.
The acoustic data in the cosmic microwave background, sonified it
Mhm.
into it ends up sounding like a very, very spooky classical
Yeah.
music piece, because the waves are like 31 light years long or something, so they
Yeah.
within the range of human hearing, and I don't think any of you guys ever heard that, but it's very cool. It sounds exactly what you think it would sound like. It's very ethereal and spooky.
Yep. Yeah. And we actually, that was done. Michele is not here, but another JPL scientist who's spent a lot of time on this project did that and created a sonification. And I think it's in the New York Times article. So if you go to the,
You can talk about on this music.
yeah, yeah, and it sounds like a soothing, like sea that's washing over you, and yeah.
There's a question from the online audience. Why is the supermassive black hole of our galaxy, quote unquote, dormant or sleeping? What makes a black hole active? I mean, I can talk about this, but you guys. I'll talk a little bit about it. So yes, it's true. The supermassive black hole at the center of our galaxy is pretty quiescent. There's not a lot going on, which is good for all of us in the Milky Way. Usually, when black hole, supermassive, well, any black hole really, when it starts having material flow into it, not just into the black hole itself, but usually piling up in what's known as an accretion disk. It kind of looks like like Saturn's rings around it. But all of that stuff, as it falls in and gets into this set of rings, this accretion disk, it loses a lot of its energy as it falls in, kind of like this gravitational potential we were talking about here. As it falls in, it loses a lot of energy, and so it tends to heat up a huge amount. It's converting its potential energy into kinetic and thermal energy. And so it heats up and it starts rubbing against all the other particles that are in this accretion disk. And that gets really, really hot. And that gets so hot that like other things that get hot, they start to glow. Like you think of an electric oven unit. And as you turn up the heat, the internal heaters inside of the oven start to glow as they get hotter, and this gets up to 10 million plus degrees, and it starts to glow and radiate and shine. And that's oftentimes how we see these things. People refer to active galactic nuclei or quasars. You've probably heard these terms. These are supermassive black holes that are actively accreting matter, and they have these bright accretion disks around them. And so we can see them all the way across the universe because they're so bright. And they also have other phenomena associated with them, jets that shoot off of them, like there was discussion of the M87, the Virgo supermassive black hole. You can see pictures taken with the Hubble Space Telescope of these jets of material. They're material that's coming from those accretion disk regions and traveling at near the speed of light out of the galaxy, and very bright and luminous. And so there's all kinds of stuff that happens when you have these feeding supermassive black holes, and it injects a lot of energy into the local region. It suppresses star formation. It's bad for things like life to develop, but it's also bad for the formation of stars and various other things.
And I'll add, the question may not have been intentionally perceptive, but it was, because it was phrased in the present tense. The supermassive black hole at the center of the Milky Way galaxy is dormant. However, as Cameron said, it's very tough for material to get into a black hole, so it tends to form an accretion disk that gets hot. There's gas near the center of the supermassive black hole that it shows the indications that a couple hundred years ago, or within the past few hundred years, something in the center of the galaxy was much hotter than it is today. And so the current explanation is that, in fact, while it's dormant today, in the not so recent past, at least according to astronomical terms, the center of our galaxy may have been looked a lot different, because the Sagittarius star, which is the name we give it, may have actually been actively accreting material. Material may have been actively falling into it.
That's right. We're running out of time. I'll take one more question from the online audience, and then one more question from the in-person. So the online audience really quickly asks, is it possible to create a small black hole in the laboratory and thus potentially create gravitational waves in the laboratory? Yeah, please don't.
Not really. We don't really know how to do that. I talked a bit earlier about analogs. People are trying to create systems that look like black holes. These are usually basically baths. These are water. So it turns out the equations that govern how water moves look very much like Einstein's equations under certain conditions. So people try to create flow of water that kind of looks like the space-time around black holes. That's the best we can do in laboratories. And yeah, even if we could, I don't think anyone would intentionally actually do it.
Well, some people were afraid that when CERN turned on and started colliding protons together, that might create a black hole. And those would be pretty small because they're made of protons, but that didn't happen, probably for the best.
And one note is that Hawking radiation, which we know causes black holes to evaporate, that's very proportional. It's like the size to the inverse, 1 over to the, so very small black holes evaporate very quickly, whereas very supermassive black holes take a much longer time, like longer than the age of the universe. But it means that if you were like CERN or the LHC to produce one of these microscopic black holes, it should, according to the Hawking radiation theory, it should evaporate rather quickly, which is good for us, as opposed to growing quickly and going to the center of the Earth and eating the Earth from the inside or something bad. So, okay, question.
So just going back to something you mentioned earlier, said if there was like a single point source of gravitational wave that you detected, it would look like a sine wave. Can you extrapolate on that a little bit more? Is that a sine wave in like would it be a sine wave in the space of like the angle correlation or in like time, or what's the?
Yeah, so it would look like in the time signal, it should look kind of like a sine wave in that domain. And so, yeah, I now realize that we're in a totally different domain than LIGO, which it would really look like a sine wave, but we'd have to convert it to residual. So I'm going to pass it to Pat.
Yeah, it's the gravitational wave signal that looks like a sine wave, and for that reason, the signal of so if you predict when these pulses arrive using the best physical models you have, and you subtract that off from the data, you get some errors, right? And those errors would look, in theory, would look like a sine wave due to this gravitational wave passing. Unfortunately, because of the gravitational waves because the pulse experienced gravitational waves around when it was emitted at the pulsar, it's not going to look exactly like a sine wave because there's something going on there that's going to modulate it, but that's going to modulate it on, again, very long timescales. So it's going to look something like a sine wave in the data that we see, but modulated by some amount because of what happened when it was originally emitted.
All right, that brings us to 10 o'clock. Let's get a round of applause for the excellent panel and the discovery that their team made. And yeah, so our next event, I guess I didn't mention this, we have an event 2 weeks from tonight, July 14th. And it will feature actually the chair of the department here, Professor Andrew Howard, talking about the Keck Planet Finder, which is this new instrument aboard the Keck telescope in Hawaii, which is one of the largest telescopes in the world, which is going to seek out, at the highest precision that we now have possible, planets, sometimes even down to Earth-sized planets around other stars. So he's going to talk about the search for exoplanets using this new instrument that just got on Keck in the last few months. And we'll have stargazing and the whole thing. And then our next Astronomy on Tap will be the following Monday, July 17th. And it's going to be all about the Euclid mission, which is this European Space Agency mission that's launching tomorrow, hopefully, is launching tomorrow. And this will be going up. It's a space telescope, effectively, that's going to be studying dark energy and dark matter throughout our universe, the things that we are called dark because we don't have a very good understanding of them, and hopefully missions like this will bring us more understanding. So it'll be two scientists from NASA JPL, Jason Rhodes and Alina Kiesling, who both work on that mission and are going to be talking about that mission shortly after its launch. So hopefully you guys can join us at that. And again, this is all on YouTube, so if you want to check out some of our past events, we've got tons of content on there from the last several years. But thanks everyone for coming, and have a great 4-day weekend.
Thank you.